I founded the trustee of French Association. Academic Secretary Mr. Ramanujan, I think the principal of Ramanujan is expected to come and join us. And members of AMTI, members of teaching fraternity, and my dear students, very good evening to every one of you. Being the coordinator of Popular Lecture Series AMTI, I welcome each one of you on AMTI and Ramanujan for today's talk by Mr. Sivaraman on conjectures and proofs. Dear Mr. Sivaraman, we look forward to the lecture on conjectures and widen our knowledge. I once again welcome the speaker.
Next, okay.
On behalf of the French Mathematics Association, I invite the August gathering to this wonderful academic event and find it a privilege to part of this lecture program to celebrate the 123rd birthday anniversary of Srinivas Ramanujan. I have been invited to all the time come here, and this was the different part of the humor just a few minutes back. Because I am Nirmala Raman, daughter of Sri P.K. Srinivasan, who established the one and only memorabilia of its kind museum for this genius mathematician, the inspirer for centuries to come for the mathematics, upcoming mathematics talents like the one who are present here, the younger generation I mean. And I welcome one and all for this event, and let us start with an invocation which conveys the meaning of perfection, and it is expressed mathematically. And the invocation is going to be done by me, so please bear with my voice. I request Ms. Kalpana, the lecturer of Anna Adarsh, to give a welcome for the gathering.
Good evening, everybody. On behalf of French Mathematics Association, I take pleasure in extending a warm welcome to our distinguished chief guest of this evening, Professor Michel Waldschmidt from France. I also welcome Professor Srinivas from Institute of Mathematical Sciences, Chennai, and Mr. Mahadevan, General Secretary, Association for Mathematical Teachers of India, Mr. Ramachandran, retired. I extend my welcome to the learned faculties, teachers, parents, students, press reporters, and all maths learning people. Thank you.
I invite Dr. K. Srinivas from Institute of Mathematical Sciences to give us a lot of these kind of events. I invite Dr. K. Sivas to introduce Dr. Michel Waldschmidt.
First of all, I would like to thank the organizers of this program for inviting me to be here. It's a great honor for all of us to have such a personality like Professor Michel Waldschmidt giving a talk on Ramanujan. And in fact, the academic circles, the research circle of India doesn't need Professor Waldschmidt's introduction because he has been visiting here, at least in my knowledge, I've been watching him for last 17 years, every year couple of times. So he's a very frequent visitor to our country. And okay, I don't want to eat up his time because if I start talking about him, I think we will not have any lecture by him. So briefly, actually all the information is there in the website that he has cited in the beginning. So about him, all the information is there, and he is quite up to date. Not only what he has done in the past, but what he is going to do for the next couple of years is also listed there. So, I would just say that he is an authority in transcendental number theory, a branch of number theory. Okay, he is one man who is, one can say that he has an authority in the subject, mastering the subject. And the other thing I would like to say that he is interested in developing mathematics throughout the country, in India, in the third world, and in the whole world. He has been traveling quite a lot, he travels quite a lot to give lectures, to conduct workshops. There is a school called Simpa School for which he is the main person. Okay, this time it is going to be in Nepal. And also the students can look at the website, his home page, to gain details about what schools are going on in mathematics. And students can attend those programs. They're quite useful. Okay, he is, just briefly, is a member of Institute of Mathematics. He is currently faculty professor in the University Pair at Marie Curie, Paris 6. He is a member of Institute of Mathematics of Juju. Okay. Mathematical Society of France, Society of Applications of Mathematics in Industries, AMS, American Mathematical Society, and Ramanujan Mathematical Society. He has been president of the Mathematical Society of France from 2001 to 2004. He has been the vice president of Simpa Schools, which is International Center for Pure Mathematics and its Applications, from 2005 until this year. He is involved in cooperation in mathematics between France and several countries, as I said, like Bhutan, Cambodia, India, Iran, Iraq, Mali, Nepal, Pakistan, Taiwan, Thailand, Vietnam, just to name a few. And he has advised, he has been the thesis advisor of about 26 students, 20 research scholars, research students, as your website says, and about 26 co-authors. He has been a member of editorial boards of Acta Arithmetica. He is currently a member of the reputed journals like Acta Arithmetica, the Ramanujan Journal, the Springer Verlag, International Journal of Number Theory, Bulletin of Iranian Mathematical Society, of which he is the associate editor, World Scientific Series of Number Theory and its applications, Annals of Mathematical Sciences, Cuba, and these are just a brief list of things. And so I would like to end here by just saying that we are very happy that Professor Waldschmidt is here and giving the talk. I request him to begin his talk. Thank you very much. Okay, before that there is something.
our traditional way of celebrating a great mathematician. It's been done by Dr. K. Srinivas. We would like you to receive a small memento from us, sir. It's with great love and affection. Let's all of us gear up to a serious lecture, which is going to be all fun and serious too.
Thank you. So it's very kind of you to have all these words to introduce my lecture. Do you hear me? Is it okay? So, as it was said, I put many things on my website. In particular, these transparencies are on my website now, and you can download them. There are two versions, one which is just to see on the screen, which is exactly this one, and another which you can print, which may be more handy if you want to look at it. So I am going to speak of Srinivasa Ramanujan. I'll just start by a few words about PKS. I had the opportunity and the honor of meeting him at several occasions, and indeed I wrote the foreword of one of his books. And he was the first biographer of Srinivasa Ramanujan, and in fact I am going to speak of the biography of Srinivasa Ramanujan. I suppose that most of you know more about the life of Ramanujan than me, but the fact that I explain the different details of his life will enable you to take use of my French accent. So I hope it will not be too difficult for you to understand. So he is born in 1887, and there were several meetings in 1987 for the 100th anniversary of his birth, and I had the chance of participating to some of them. He went to school in Ramanujan from 1894 to 1903, and in 900 he began to work on his own on mathematics, summing, geometry, and arithmetic series. So he was in Ramanujan, and I can just show you a few pictures of Ramanujan. I went a few times there, and this is the temple where this is the house Ramanujan with a well on the back side, and the house like it is now with the statue of Ramanujan, and there is a door which goes to the room, which is the room there, a very simple house. This is the town high school of Ramanujan, where Ramanujan has been working for many years, studying. And this is where he got as a prize a book by Carr, the synopsis of elementary results, a book on pure mathematics. And there are 5,000 formulae in this book, and the style of the book is the style that Ramanujan was going to use for his work. The kind of problem that Ramanujan was able to solve in town high school in Ramanujan is the following one: find two numbers x and y, such that the square root of x plus y is 7, and x plus the square root of y is 11. And, well, this is something which is not that easy, but Ramanujan found easily a solution, which is 9 for x and 4 for y. So the square root of 9 is 3, and 3 plus 4 is 7. The square root of y is 2, and 9 plus 2 is 11. In 1903, in December, he passed the exam at Madras University, and in 1904, just after, he entered the government arts college in Ramanujan. He got a prize, and he got at the same time a scholarship, Subramanian scholarship. There are many sources of information on his life. For example, if you look at the MacTutor History of Mathematics, and the address is here, it's written that Ramanujan began to undertake deep research in 1904. He investigated the series sum of 1 over n, which is called the harmonic series, and he calculated Euler's constant to 15 decimal places. He began also to study the Bernoulli numbers. Also, this was entirely his own independent discovery. So this is what is written in this website, and I will just give you a few information on what is the series and the Euler constant, and what are the Bernoulli numbers. The harmonic series is the sum of 1 over n. If we stop the sum, if we truncate to an integer capital N, we find this finite sum. And to compute this finite sum is not so difficult. To estimate this finite sum is not so difficult if you use a geometric picture and you replace 1 over n by the area of rectangle with length 1 and height 1 over n. And doing that, if you compute some area, you have to compute an integral. But these integrals are much easier to compute than the sum. And this gives a proof, not difficult proof, that the limit of Sn minus log n exists, and the limit is Euler constant. So this is the definition of Euler. Now, this Euler constant can be computed, and it's called also Euler-Mascheroni constant, and the value is given here. If you have some number that you want to know the value of a sequence, a good reference is the Encyclopedia of Sloan. This is Sloan, which is on the internet, and there is plenty of information on the constants and sequences. I mentioned Bernoulli numbers. There are several mathematicians with the name of Bernoulli, and the Bernoulli numbers comes from Jacob Bernoulli. And they are defined by what we call an induction. The first Bernoulli numbers is 1, and then you have a formula. So I know that the symbol nk is not used everywhere in the world in the same meaning. This is the number of combination of n by k, n choose k, like we say. Sometimes it's written cnk. Okay, so if you prefer to be more precise, if you take this formula for n equal 2, you stop at n minus 1, so you stop at 1. The formula is b0 plus 2b1 equals 0. You know b0, so you can compute b1, which is minus 1 half. The next formula is b0 plus 3b3 plus 3b1 plus 3b2 is equals 0. This gives you b2, and you can compute that. So these were studied at the end of the 17th century by Bernoulli, but Ramanujan discovered these numbers himself and studied them. In 1905, he failed the final exam, and he entered the college Pachayapa in Madras in 1906. He was ill after that, and he went back to Kumbhakonam, and in 1907, he failed the final exam. In 1908, he studied continuous fraction and divergent series. Continuous fraction is a fascinating subject, and I am going to teach a full course in 1 month on this at another place, but I will not mention it here, but it's a very interesting topic. In 1909, he underwent an operation, and he married with Janaki Amal in 1909. I had the opportunity of meeting S. Janaki Amal when there were the celebrations of the 100th birthday of Srinivasa Ramanujan. In 1910, he met Ramaswamy Iyer, and in 1911, he published his first mathematical paper. He got a position as a clerk office in the Madras Port Trust, and he got also a scholarship from the University of Madras, which started in 1930 for 2 years. In 1912, he found a solution in 1912, he found the solution to two problems which were asked, two questions which were asked in the Journal of the Indian Mathematical Society. The first one is this number. You compute the root of a number which is 1 plus 2 times the root of another number, which is 1 plus 3, the root of any continued length, with 1, 2, 3, 4, and so on. And here you start with 6, 7, 3, 9, but here you have 2, 3, 4. So you have the sequence of integers 2, 1, 2, 3, 4, and then you have the sequence 6, 7, 8, 9. So this is the rule to produce these numbers. And he found the solution. And the solution for the first one is 3, and the solution for the second one is 4. These are quite interesting exercises, and it's quite interesting to see how we did it. So you start from the fact that n plus 2 squared is 1 plus n plus 1 n plus 3. I think this is not too difficult. You have n squared plus 4n plus 3 here, n plus 1, which means plus 4. What you do is that you take the square root of both sides and you multiply by n. So the square root here is n plus 2, you multiply by n. You take the square root, so you take this number, and you multiply by n. So you have this formula here. Okay, so you have here n plus 2 and here n plus 1 and n plus 3. This looks more or less the same. If you replace n by n plus 1, then n plus 2 becomes n plus 3. Which means that if you define the function f of n to be the left-hand side, n plus 2, what you have here is n plus the square root of 1 plus f of n plus 1, which is written here. F of n is the left-hand side, n is here, you have the square root, and you have 1 plus f of n plus 1. And so you have the formula for this function f. And this formula can be written as follows: f of n equal n times the square root of 1 plus f of n plus 1. But f of n plus 1 is n plus 1 times the square root of 1 plus f of n plus 1. So if you do that, you see that you can continue and get, by replacing n times the root of 1 plus n plus 1 times the square root of 1 plus n plus 2, and so on. And it looks like the question which was asked, and in fact, if you take the value 1 here, you have 1, 2, 3, 4, and so on. And so you compute f of 1, not using this formula, of course, but using n plus 2. N plus 2 for n equal 1 is 3. So this is a proof. Now you may ask, why did I put quotes here? Is the proof complete? When we want to do mathematics, we have to check each step. And I think all the steps to here are correct. All this is absolutely without problem. But the small dots here have some problem. You can define the sequence when you stop, and then you have to check that this is a convergent sequence. And it's possible to prove it, it's true, and then you complete it. But this small dot requires some explanation. It is the same for the second problem. You start with n plus 3 squared. You write n plus 5 plus n times n plus 1 times n plus 4. Like this, you have 4 plus 4, 5 plus 4, which means 9 here. And otherwise, you have n squared plus 6n. And then you take the square root of the two sides. You multiply by n, so it's very similar. And you have here n plus 3 and here n plus 1 n plus 4. So this is the value, the same as this one, but you replace n by n plus 1. So you define now g of n equal n plus 3, and you write this formula as g of n equals n times the square root of n plus 5 plus g of n plus 1. You replace g of n plus 1 by this formula, but the n here should be replaced by n plus 1. So this becomes n plus 1. This, instead of n plus 5, is n plus 6, and here you have g of n plus 1. am I going too fast? I don't know. Is it too fast or?
The pace is okay.
Just complain.
It's okay.
And so you do the same as him, okay? You can continue. And then you replace n by 1. And what you will get here is exactly the formula which was asked, the question. And then you can get it. So this was the exercises which Ramanujan was able to solve. In 1912, he wrote a letter to a professor in England, and this letter was sent to the professor Hill. And in his letter, Ramanujan wrote that 1 plus 2 plus 3 and so on is minus 1 over 12, that the sum of the square is 0, and that the sum of the cube is 1 over 120. So these are some of the formulae that Ramanujan wrote in his letter. And the answer of Hill came very fast the same year, not as fast as electron made, but it was rather fast, given the conditions. And Hill said that these formula are completely wrong, because he said if we stop the sum at n here, we know the value which is 1 half of n plus 1. I suppose you know that, it's easy to do. This one is a little bit more tricky, but not so difficult. If you stop at n squared, when you solve the square, you find n to n plus 1 values, n plus 1 is 6. And here you have n plus 1 over 2 squared for the sum of the cube. So he just said that this formulae of Ramanujan made no sense. Well, we should not blame him because he answered. And some of the other people to whom Ramanujan wrote did not answer. The series that Ramanujan were considering are divergent series. And there are several ways of renormalizing divergent series. And in particular, Euler had worked a lot on this topic. Euler wrote the introduction analysis in Newton, so the analysis of infinity in 1748. Hardy wrote later in 1949 a book on divergent series. And if I have time at the end of my talk, I will come back to this book. It's very interesting. I did not know it very well, but thanks to the fact that I was giving this lecture, I went to the library in Math Science, and it's very interesting. In the foreword, in the introduction of this book, Hardy quotes Abel. And Abel wrote in 1828, 1 year before he died, divergent series are the invention of the devil, and it is shameful to base on them any demonstration whatsoever. And it's very interesting because Abel was a great mathematician, so that this was the feeling at that time. So I told you that Ramanujan wrote to other mathematicians in England, Baker and Thompson, but there was no answer. So Ramanujan continued to write, and he sent a letter to Hardy on the 16th of January 1930. And it's quite a remarkable letter. In particular, he said the following: I have had no university education, but I have undergone the ordinary school course. After leaving school, I have been employing the spare time at my disposal to work at mathematics. I have not trodden through the conventional regular course, which is followed in a university course, but I am striking out a new path for myself. I have made a special investigation of divergent series in general, and the results I get are termed by the local mathematicians as startling. So this was what he wrote. And Hardy was a great mathematician, one of the greatest mathematicians that time in England. And Hardy was in Cambridge, and there was another mathematician, very influential at that time, Littlewood, who was a close collaborator of Hardy. And there is something which is called the Hardy-Littlewood method, or the circle method, which the main basic ideas are in fact due to Ramanujan. In his letter to Hardy in January included also some divergent series. One of them is 1 minus 2 plus 3 minus 4 is 1/4. And the other is the sum of the alternative sum of the factorials. And he found the value 0.596 and so on. Again, I prepare something at the end to explain this formulae. But the second one is quite interesting because Euler himself studied the same formulae and found the same value. And of course, these are divergent series. And to compute this number, to give him a definition and compute it, it's quite tricky. The answer from Hardy was quite different from the previous answer. And you see that it was sent very fast. I was exceedingly interested by your letter and by the theorems which you state. You will, however, understand that before I can judge properly of the value of what you have done, it is essential that I should see proofs of some of your assertions. It was not the kind of thing to send to Ramanujan because this was precisely his problem. He could not produce proofs. Your results seem to me to fall into roughly 3 classes. There are a number of results that are already known or easily deducible from known theorems. This is probably for Hardy the case of divergent series. So he knew enough of divergent series to consider that this was something known. There are results which, so far as I know, are new and interesting, but interesting rather from their curiosity and apparent difficulty than their importance. And finally, there are results which appear to be new and important. So this was the beginning of the collaboration between Hardy and Ramanujan. There was a new letter from Ramanujan to Hardy on February 27. So you see that this letter was February 8, and the next one February 7. In 1913, Neville, a colleague from Hardy from Cambridge, visited India. And from March 17 to April 14, Ramanujan traveled to Cambridge. He became Fellow of the Royal Society in 1918 and also Fellow of Trinity College, Cambridge. And he traveled back to India in 1990. By the way, there may be some mistakes in my presentation, so if you know some mistakes, please tell me. I wish to correct it. During his stay in Cambridge, there was a story which is recorded in Hardy's obituary to Ramanujan, and it is the famous taxi cab number, 1729. And what Hardy writes about that is the following: I had written the taxi cab number 1729 and remarked that the number 7 times 13 times 19 seemed to be a rather dull one. It's interesting because it means on one hand that Hardy used to decompose into prime factors the number that he saw, and it's not that easy to decompose this number into prime factors. But also Hardy missed a lot, and he said it very frankly. What Ramanujan answered is that this is not at all a dull number. It's a very interesting one because it's the smallest positive integer, which is the sum of two cubes, two positive cubes, in two different ways. So it is 1 plus 1728, which is 12 to the cube, but it is also 729, which is 9 to the cube, plus 1000. Immediately Hardy asked another question, which was, and what about the smallest number, which is the sum of two squares in two different ways? It's interesting that Hardy asked this question because there are many other questions that could be asked. Of course, there is one which is easier, and probably Hardy did not ask because he immediately answered, which is, if you replace the cube by the square, what will be the smallest solution? And the answer is 50. 50 is 7 squared plus 1 square, and it is 5 squared plus 5 square. So for the squares, it is easy. So you see that it's growing rather fast. It's 4,104 for the next example. So the question of Hardy was about fourth power. And the answer of Ramanujan was, after just thinking a little bit, that it is probably a rather large number. And again, Euler comes into the picture, because Euler had investigated this question and found that the smallest number is this one, and indeed it is a large number. It is the sum of two fourth power in two different ways. The kind of problem we are looking at is related with Diophantine equation, representation of a number by sum of powers. Ramanujan studied also the numbers which are cubes and which are sum of three cubes. And there is one solution which is 3, 4, 5, 6. But when you want to check 3 squared, 3 cube plus 4 cube plus 5 cube is equal to 6. And again, a parametric set of solutions. So if you replace A and B by integers, you get infinitely many solutions x, y, z, w. Another equation that Ramanujan studied quite extensively, and I will say a few words about it, is called the Ramanujan-Nagel equation. It is x squared plus 7 equal to 2 to the n. So there are two unknowns. X is an unknown, a positive integer, n also is an unknown. So the question is, you take a square, you add 7, and you ask that the sum is a power of 2. And Ramanujan knew the solution which are here. If you take x equal 1, you find 8, which is 2 to the cube. If you take x equal 3, you find 16, which is the power of 2. And x equal 5, you have 32. X equal 11, you have 128. And x equal 181, you have again a power of 2 to the 50 when you add 7. So Ramanujan just made this remark, and it's a quite interesting remark because it yields some very interesting developments. First of all, it's not that easy to find these solutions. And also, it's an interesting result due to Nagel only in 1948 that there is no further solution for this particular equation for if you take t equals 7 here, there is no other solution. In 1960, Roger Perry studied this equation when t is a positive number which is not 7. And he found that in this case, this equation has at most two solutions. So it's very interesting that Ramanujan found the only value of t, which is t equals 7, for which the equation has more than two solutions. And indeed, in this case, there are comparatively large number of solutions. When we do mathematics and research in mathematics, we like to ask questions. And the natural question is, are there examples with two solutions? And the answer is yes. And here are some examples. If you take d equal 23, if you add 3 squared and 23, you find 32. If you add 45 squared and 23, you have 2048. So with d equal 23, you have two solutions, x and n. But also you have a parametric set of solutions, so an infinite family, which prove that the result of Apéry is the best possible. There are infinitely many cases when there are more than just two solutions. And again, when we see this kind of results, we ask another question. these cases. But is it a complete list of the cases where there are two solutions? And the answer is yes. And this was done by Beukers in 1980. In all the other cases, there is at most one solution. And then it's essentially complete because you just take the value of n and you take any value of x and you take the difference and you find the value for t. So one solution occurs. There are further things to say on this equation when d is negative, and Michael Bennett has worked since 1995 to consider this solution and to solve it essentially. Ramanujan has worked a lot on what is called the partition of a number. So let me define what is a partition. When you have a number, you want to write it as a sum of smaller numbers. So let me consider the number 4. You write it 4, just itself, so this is one partition. But you can write it 3 plus 1, 2 plus 2, 2 plus 1 plus 1, 1 plus 1 plus 1 plus 1. So we say that the number of partition of 4 is 5. 1, 2, 3, 4, 5. You have to be precise on how you count the number of solutions. Because when you write 3 plus 1, it's also 1 plus 3. So you have to say the rule why you count 3 plus 1 and not 1 plus 3. So you take decreasing the sequences of parts. So this is the start of the sequence, 1, 2, 3, 5. And it continues with 7, 11, 15. And the table of the first 200 values have been computed by McMahon. This set of this sequence, 1, 2, 3, 5, 7, 11, 15, is also on the encyclopedia of Zero. Congruencies for these partition numbers. If you count the number of partitions of a number, which have the property that when you divide by 5, the remainder is 4. So 5n plus 4 means that the decimal way of writing this number ends with either 4 or 9. So if you take a number where the last decimal digit is 4 or 9, then the number of partitions is a multiple of 5. And then for 7n plus 5 is 7. And for 11n plus 6 is a multiple of 11. He gave also some other congruencies. Here, these congruencies are modulo prime numbers, and here they are modulo square prime numbers. So he studied extensively this set of problems, and again he's on the path of Euler without knowing it. Euler gave some formula for the partition number, and when you take what is called the generating series of the partition number, which means that you multiply p of n by x to the n, and x may be just a symbol, or it may be a complex number if you wish. And you may ask that this complex number has modulus less than 1 if you want to work with convergent series. Then this series can be written also as a product. And the product is one of the 1 minus x, 1 minus x squared, and so on. So this formula here can be written as here. One with the sum of p of n x to the n is a product. The product is the product of 1 minus x to the n, and it is the inverse because it's 1 over. You see this formula, each series on the left-hand side and a product on the right-hand side. So it says that the series is equal to the product. It's one of many examples of what is called Eulerian product. And the more famous example is given by the Riemann zeta function, which is the sum of 1 over n to the s, but it is also the product of 1 minus s equal to minus 1. This function was studied by Riemann when s is a complex number, but Euler studied it especially this formula when S is a real number. And in fact, Euler studied it for S positive real number or a negative real number. Another example of the Euler product is obtained by looking at the Ramanujan tau function. To define this function, I start with x over 1 minus x, which is the sum of x to the n. For n equal 1 to infinity, we multiply by x to start with 1. So you start with this formula, and now you can take the power of this, because you start with 1. There is no constant term. And so, if you take the product of this with the exponent, so n, and you take the power of 24, this product that you obtain can be decomposed into a series, and the series is called the tau function of Ramanujan. So this is in fact the definition of the tau function. And you see that you have an infinite product on the left-hand side, and a sum on the right-hand side. So it's an example of the Eulerian product. Another example is if you take the sum of tau of n divided, well, this is more the Eulerian product, tau of n divided by n to the s, you have a product which looks very much like the product for the zeta function. So the congruencies which were studied by Ramanujan are that tau of Pn is divisible by p for p equal to 2, 3, 5, 7, and 23. And he got also some congruencies by modulo 691. And this number is the numerator of the Bernoulli number. This is why the tau function has some very interesting properties, and one of them was conjectured by Ramanujan. And it was a challenge for many years, and finally it was proved by Delin in 1974, and this, the result of Delin is this one. Tau of p as a modulus, which is bounded by 2 times the square root of p to the 11. There was a lecture by Serre on Delin's work, and Serre explained that when there is a conjecture, and when someone proved that this conjecture is the consequence of another conjecture, and this is what the said, proved as a first step, he explained that this conjecture of Ramanujan was a consequence of Feyn's conjecture. And then if someone solved the Ramanujan conjecture, then the theorem should be have two names. And then was the one who solved Feyn's conjecture and proved that Feyn's conjecture was a consequence of it. The work of one of the many works of the collaboration between Hardy and Ramanujan is the following. For almost all integers n, the number of prime factors of n is log n. So you know that the way of writing mathematics from Ramanujan was not exactly the one of Cauchy and the people who introduced the convergence. And we need to explain what it means for almost all. But this is much easier than to explain what is the divergence series. Almost all is a precise meaning in number theory. We count the number of integers n that are x is the upper bound, for which the number of prime factors of n, so it is written only of n here, this is the number of prime factors of n, is between 1 minus epsilon log n and 1 plus epsilon log n. So it's log n up to the constant 1 minus epsilon and 1 plus epsilon. So we count how many integers there are n. If all the integers were satisfying this, then the value of a of x will be x for the integer part of x. But what almost all means is that if you divide by x and you look at the limit, then the limit is 1 when x tends to infinity, and this is true for all given psi. So this is the precise meaning of the sentence which is there. This sentence deals with the divisors of an integer, And there is an interesting paper by Ramanujan on highly composite numbers. I give the definition and then I will give you some conclusion. What you do is that for all the integers, you count the number of divisors. And you look at the record, the numbers which has more divisors than all the previous ones. Okay, you start with 2, the number of divisors is 2. Next is 3, that the number of divisors is 3 is just 2, so it's not better than 2. Next is 4, the number of divisors is 4 is 3, divisors are 1 and 4. So it's better than 2. So 4 is highly composite. 5 is prime, the number of divisors is 2, so it's good. 6 has 4 divisors, so it comes here. Now if you go to 7, 8, 9, 10, 11, the number of divisors is not more than 4. So you forget them, but 12 is 6 divisors. And you continue like that. So you have the sequence of integers, and again it is on the Sloan encyclopedia. And in this paper on highly composite numbers, Ramanujan made a mistake. But it's a mistake which is quite understandable for him. He used the fact that if t is a real number, if 2 to the t and 3 to the t are integers, then t is an integer. I repeat, you have a real number t. You assume that 2 raised to the power t is an integer. And you assume also that 3 raised to the power t is an integer. And conclusion that t should be an integer. If you take an example, you take the number t, which is the logarithm of 1000 divided by log 2. If you compute 2 to the power t, you find 1000. But if you compute 3 to the power t, then check it is not an integer. And so for Ramanujan was something confused. And the PhDs, Ramanujan and Erdős looked at this paper, and they were not able to prove that it is an integer. So they asked Siegel, and Siegel said, this is a very difficult problem. And in fact, I started to work on this problem in 1969, and I have been working on this for 40 years, and it is still a no. It's really a difficult problem. So what Ramanujan did in this paper is not complicated with some small gap, but it was sure it will be proved. Ramanujan used a formula for an approximation for pi, and one of the formula is this one. You have this number which you compute with the square root, and you find a number which looks like pi to a very high accuracy, and you have the digit which is defined as this pi. It is known that the number pi cannot be written in a form which is similar to this pi. The numbers which can be written like this are algebraic. It means that they satisfy some polynomial equation. And pi does not satisfy such an equation. So you will never get equality. But it's very close to equality. He gave another formula on pi, which is this one. And this formula is remarkable because if you take any, you have an infinite sum, which is convergent to the science of Cauchy. And if you take just the first one, you already have 6 exact digits for pi. If you add one value to n, you add 8 more decimal digits to your computation. So it's quite remarkable. I just give another formula for 1 to pi, but I will come back to this formula because this formula was used in the and the number of decimals which were computed was at this time 17 million decimals. Many people have looked after that to this. In 1999, the number of digits which were decimal digits was 2 followed by 10 zeros, and in August 2009, so very recently, the number of decimals which were computed was 2.5 trillion decimals. So 2 followed by 12 zeros. And so this was in Japan very recently. A few words about the Ramanujan notebooks. They were written from 1903 to 1940. And I have seen the original of these notebooks in the library in Madras. There are 3 notebooks. The first one has 154 pages, the second 252, and the third one has only 33 pages. And they are going to be edited and put on the internet before the International Congress of Mathematicians in August. So very soon they should be available. There is also a very interesting story with the lost notebook. It was a notebook which was found by John Andrews in 1986 in the library of Cambridge, and it was edited by Bruce Grant from 1985 to 1987. They have worked a lot on the book of Ramanujan, and they could explain many things which were not at all easy to understand if you just look at the notebook without the reading. The last book of Ramanujan, one on the so-called work data. This function started to be understood only in 2000, so more than 100 years after Ramanujan passed away. And there is an important paper written by Traders on the work data functions in French Mathematician, which was published in 2001. Work data function is a subject which was mysterious in many years until this work, which was done by a student of Gonzague. And Gonzague has studied the work of Ramanujan very deeply to revise this student. Next Tuesday, so on December 22nd, for the birthday of Ramanujan, there will be an international conference in Tumbakona, number 3 in work data functions. And at the occasion, the Sastra Ramanujan Prize will be given to Catherine Wisman, who has worked precisely on work data functions. This Ramanujan Prize from the Sastra Foundation, Sastra University, was created in 2005. And it's interesting for you to see who got the prize, because these are young mathematicians, they should be more than 33 years old. And all of them are very bright mathematicians, quite remarkable. The first ones to share the prize were Manju Bhatyava and Kanal Sundararajan in 2005. Sundararajan here, Dallas. In 2006 it was Terence Tao, and in 2007 it was Ben Green. Tao got also the Fields Medal, and Tao and Green collaborated to solve an important problem on arithmetic progression problems. They proved that there are arbitrarily long arithmetic progression problems, which was a very big challenge for them. And last year, the prize was given to Akshay Venkatesh. So I give you a few references on this topic if you want to know more. There is a paper there is a talk by Gonzague from Ramanujan to Hardy, from the first to the last. I attended this talk that he gave in Paris, and on the website of the French Mathematician Society, you can find some information which was collected for this occasion. I already mentioned the fact of the history of mathematics, and there is another source of information on mathematics, which is Wolfram research website of the Lifetime. And also, we have the free encyclopedia of the Wikipedia. The wiki encyclopedia is something to use by being careful. You should not believe that what is said there is true. anybody can contribute and make good things which are wrong, but it's a good source of information, provided that you can check it from other sources. And just to give a few examples, I wish to give you some more information about what you find on this encyclopedia under the name of Ramanujan. They say that the is known for several topics, and many of them have his name, like the Landau-Ramanujan constant, Ramanujan prime, Ramanujan soluble constant, Ramanujan interaction, Ramanujan sum, and Rogers Ramanujan mechanism. I know most of them, but for example, I did not know at all the name of soluble, and I learned it yesterday when I was preparing this lecture. So I give you a few information